Hi, everybody, and welcome back. This is Chapter 10 we're starting, and this is going to be on hurricanes. And you can sort of think of Chapter 10 as being kind of an extension of Chapter 9. Of course, in Chapter 9, we talked about the atmosphere and air pressure and storms, of course, but really we're going to focus more on pressure differences in this chapter. So where we talked about pressure differences in Chapter 9, air flowing from high to low, something called the Coriolis Effect. We're going to focus on that more this chapter, especially as we talk about hurricanes and cyclones in general. This video is going to be just section 1, although I will include a couple of extra things. First of all, this diagram right here we're going to mark up, so I should have given it to you, or you should have access to it. I'm also going to talk a little bit more about the Coriolis effect and mark up this picture of the northern hemisphere of the United States and talk about why the Coriolis effect actually happens. Lastly, I'm going to finish out this section 1, with a short video from The Simpsons, wherein they describe the Coriolis effect, and we see how that creates all kinds of problems in the world of The Simpsons. So I think you'll like that. So anyway, let's go ahead and get started. Chapter 10. Well, like we always do, or almost always do, we start with some sort of a case study, and we are going to be looking at Hurricane or Superstorm Sandy, as it has come to be known, in more detail a little bit later on. But this is just sort of a prep to get you thinking about that. Usually, when we talk about damaging hurricanes, we talk about Katrina, and of course, that was one of the most damaging in terms of property as well as people's lives in history. But Superstorm Sandy, being more recent and being a little bit more weird in terms of circumstances, is also a case study that we can talk about. It was only about a week between when it formed to when it made landfall, and it took a kind of a weird track. Most hurricanes don't hit New York City or New Jersey, but Hurricane Sandy definitely did. Like I said before, it had an atypical path, and it also kind of had an interaction with a cold front from the Arctic that made it into this giant monster storm that we really were not expecting. It wasn't hurricane force winds when it made landfall, but it was just enormous. It was a monster, and it was very, very, very expensive in terms of property damage and things like that. Not really in terms of lives, but you heard the stories of all kinds of properties on the East Coast, especially oceanfront, just being absolutely destroyed, and the Jersey Shore especially took a big, big hit. It also resulted in some snowstorms in other areas, and the corresponding power outages too. So all these things together really made Hurricane or Superstorm Sandy, as it came to be known, really, really a monster. So we've got some photos from New York City. It looks like a museum type place right here, where the bottom floor has got a foot or so of water, and the floor is all ruined right there. And of course, you probably remember seeing all these images from the Jersey Shore. This looks like it could be, I don't know, Ocean City or Long Beach Island. All right, one of those places out on the barrier islands off the Jersey Shore. And the storm surge just washed right over those islands right there and dumped all kinds of sand and really destroyed a lot of homes. So we're going to be looking at Sandy in more detail a little bit later on, and kind of what we learned from it. But for right now, let's go ahead and just kind of define what we mean by hurricanes. And when we say hurricane is actually kind of a specific name. Really, the more general name for it is cyclone. Oops, I didn't mean to move that. Is a cyclone. All right, a cyclone is a center of low pressure with rotating winds, which is why we oftentimes call tornadoes cyclones. So a cyclone, let's see, I'll write it right here. C-Y-C-L-O-N-E, could be a hurricane. All right, center of low pressure with rotating winds, a tornado. They're also given other names around the world. In the North Pacific, off of Japan, they're called typhoons. And cyclones in the Indian Ocean are also given the very unoriginal name of cyclone. So cyclone could mean a general term, or it could mean a specific storm in a certain area. So all these different names refer to, or a cyclone could refer to any one of these different names. In the Midwest, they oftentimes call tornadoes cyclones, twisters. All right, so the center of low pressure with rotating winds. All right, and depending on which hemisphere it's in, it always spins a certain way. In our hemisphere, in the northern hemisphere, it always spins counterclockwise. And of course, it's opposite in the southern hemisphere. Clockwise. Let's make that a different color. Make that blue. All right, clockwise in the southern hemisphere. I'll explain why that is in just a second. It can be tropical, that is within 23.5 degrees of the equator on either side, or it could be extratropical. Sometimes we call it subtropical. All right, that we are sort of in a subtropical area right here. That is the mid-latitudes. All right, so depending on where it forms, where it originates, and what the temperature is of it, we're going to see later on how warm water and warm air really feed these storms. That'll determine if it's a tropical storm or an extratropical storm. But many of them are tropical because, like I said, it does depend on warm water and warm air. All right, and so wind speeds really determine how we characterize them, how we categorize these storms. And this right here, that is a typo. That should say lowest atmospheric, not temperature, because I just got done saying that these storms are fed off of warm temperatures, right? Sustained wind speeds and lowest atmospheric pressure, it should say. Lowest atmospheric pressure. Like I said before, these are centers of low pressure. And so the lower the pressure in the center, the greater the wind speeds are going to be. All right, this right here is an example of a hurricane. You can see this kind of counterclockwise rotation towards the center. All right, and so we have these forces that are kind of all acting in concert with each other to cause this counterclockwise and inward motion. So what are these forces? Well, there's a pressure gradient. All right, well, what's a pressure gradient? A pressure gradient, or a gradient, is a change in something over a distance. All right, so for example, I have these lines right here, all right, and they represent a staircase. All right, so this is the highest, and this is the lowest stair down here. You could call that a height gradient. All right, so you're stepping down high, lower, 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 lowest. All right, well, pressure does the same thing. You can have an area of high pressure and low pressure, and wherever you have pressure differences, this is all one pressure, that's all one pressure, that's all one pressure, just like that's all one stair, that's all one stair, that's all one stair. All these pressures are kind of the same along these lines right here. We call these lines isobars. Iso means same, and bar comes from the same word that barometer comes from, or barometric pressure. That refers to pressure. So it means same pressure, same pressure, same pressure. Just like every stair is the same height, same height, same height. That means that as you cross these lines, you go from either high pressure to low pressure or low pressure to high. And so we call this a pressure gradient. As a result, things always flow, well, usually from high to low. And so where you have a pressure gradient, the air is going to want to move across those imaginary lines from high to low. That's what in fact, I should have made that blue, shouldn't I? Because that's what the pressure gradient is colored right there. Okay, so wind always wants to flow across pressure gradient lines from high to low, perpendicular to them, right? Because if this is highest, this is lowest, it's going to go straight perpendicular to them. But then we have the Coriolis effect, or the Coriolis deflection. All right, and what that means is that any wind, or any fluid, I should say, that wants to move in a certain direction, the Coriolis effect will always bend that off to the right in our hemisphere. Now, stick with me here. You're saying that's not the right. Well, yeah, but the arrow is upside down. If you were to turn that upside down, that would be the wind that wants to flow from high to low bending off to the right. All right, so turn your head around, and that'd be the right-hand side. The Coriolis always bends things to the right in our hemisphere. And I'll show you why that is. So let's say that that you're standing on the equator. So you're right here. Okay? And your friend is at the North Pole. So your friend is up here. Okay? It's not a very good friend, but there you go. And you have a baseball in your hand. So make the baseball, oh, I don't know, make it green. All right? And you want to throw the baseball to your friend who is at the North Pole. All right? Well, before you throw it, you need to keep in mind that if you're at the equator, you're moving faster than you are at somebody at the North Pole. Because remember, every place, like, let's see, this line right here, that's one of the meridians. All right? Every meridian goes around the Earth at the same rate, right? Every place on the meridian rotates around the Earth once every 24 hours. So that means if you're going around the widest part of the Earth, you're traveling a lot faster than somebody who is closer to the pole. See this up here? It's a smaller arrow. Okay? So since you're going faster, you've got more momentum. And so if you try to throw a ball directly to somebody at the North Pole, that ball has more momentum, sorry. And as a result, you've got momentum going from the equator to the pole, and so that ball is actually going to miss your friend and curve off to the right-hand side like that. Similarly, if your friend, let's say your friend had the ball now, all right, and there's the ball in your friend's hand, and they want to throw it to you, they are moving slower than you are. All right, so if they try to throw it to you straight down from north to south, well, by the time it gets to you, you will have moved further because you're going faster. And so the ball from your friend coming to you is going to, oops, I don't mean to make that green. It's going to bend off to the right as well because they're moving slower than you. So that's true of any fluid in the northern hemisphere. That is water or a gas. All right, so we call this the Coriolis effect because the equator is moving faster than the poles. You have this curvature off to the right of the direction that you want to travel. All right, we call it the Coriolis effect. And so what that does is that affects the direction that wind is going to want to flow. So I'm going to ask you to turn your attention now to the diagram that I showed you earlier. I think I did, like this. Okay. All right, this is wind directions around cyclones and anticyclones, and I'll describe what the anticyclones means in just a second right here. But I realize that this looks like a bunch of lollipops, but these are actually pretty meaningful symbols right here. One thing that I need to tell you about is what MB means right here, and that is a unit called millibars, millibars. You probably recognize milli as being the prefix that means 1/1000th. And what is a bar? Well, a bar is the same word that barometer comes from, and isobars and barometric pressure. So 1 bar equals really the weight of 1 atmosphere. Okay, so since you live at the bottom of the atmosphere, you are experiencing 1 bar of pressure, and so that can be broken up into thousandths. And we say right around at the bottom of the atmosphere where we live, the pressure kind of hovers right around 1,000 millibars. All right, so that's what these increments mean right here, these numbers. All right, now why are there only 2 numbers? Well, because for the sake of space, I cut off the first 1 0, and only the second 2 numbers are in there. So for example, this let's see, this right here, that would be 1,000 millibars. All right, that would be 1,028 millibars right there, and so forth. All right, so I'll explain in just a minute or a couple minutes, what these lines mean right here. But what we want to do is we want to draw isobars. All right, we want to draw lines that connect areas of equal pressure. And it's almost like connect the dots, sort of, but you need to do a little bit of interpretation right here. So where's the highest number on here? Well, there's a 96 right here, but I'm actually going to tell us to ignore that for just a second. Aside from the 96, the highest number is 28. right here. All right, so the highest pressure is really over on the left-hand side. So I'm going to put a big H right there. I'm going to write it in blue. It's our H. And that's our highest pressure. So what we want to do is we want to draw isobars, that is, lines that connect areas of equal pressure. Well, since that area in the middle is the area, the center of high, what I'm going to do is I'm going to draw kind of concentric, or like a circle that connects those two weather stations that have that pressure right there. All right, so that suggests that everywhere along that line it's the same pressure. In towards the center it may even be higher, but as far as we know, that's the highest pressure line we can draw. So it says to draw them in 4 millibar, that's what MB means, intervals. So that means the next one down should be 1,024, right? So let's find the 24s here. We've got one here, and here, and here. So I'm going to draw it like this. So you might say, well, Mr. Mounts, how did you know not to go around that one, or how did you know to take that path right there? Well, even where we don't have data, look at these two stations, here and here. That's 1,028. That's 1,020, and so it's got to be 1,024 somewhere in between. And so you can sort of interpret where those lines should go, even if you don't have data. Here's another 28. There's another 20. So 24 has to go in the middle. Remember, these lines are kind of like stairs, represent the edges of stairs, and as you step down, it goes from high to low, but all along the edge of that stair, it's the same height. We could think of it as the same way. So all these lines right here are the same pressure. I'm now drawing a 1,020 millibar isobar. Right? Millibar is the unit, and isobar is the actual line. Iso meaning same, means same pressure. All right, so there's our 20 right there. Did I miss any? No, I don't think so. All right, 16, 1,016. Connect the 16s, not the 12s, right? There we are, and then the 12s are all the way on the outside. That's pretty easy. So they're not perfectly concentric, but for the most part, it is. All right, now let's look at the right-hand side now. Now I'm going to draw in red. I said before that this right here is not the highest pressure, but it's actually the lowest pressure right there, 96. Wouldn't say, why wouldn't that be the highest pressure? Well, remember I said the atmospheric pressure hovers right around 1,000. So that's not 1,096, but what is that? It's actually really low. It's 996. So it's actually below 1,000. So it's really a low pressure right there. So there's no other 96 to connect that to, so I'll leave it all by itself. But I will connect, what's the next increment up? What's the next interval? Well, 4 up from that, right? 1,000. And so we have a couple thousands right here that I can connect in a concentric circle like that. What do we go up from 1,000? We go up to 1,004, right? 1,004, like so. And then 1,008, which is all the way out here. All right, and this is a very common configuration. All right, we've made 2 sets of concentric circles, a center of high pressure and a center of low pressure right here. Now, let's ask ourselves, what direction does the wind want to flow? Well, remember we said before when we talked about the pressure gradient, that is, these lines are the pressure gradient, almost like stairs stepping down. Air always wants to move directly across from high to low at all times. All right, straight across, perpendicular. That's the pressure gradient force right there. Remember, gradient meaning a change over distance. All right. So air always wants to flow from high to low, so it's going to flow out of the area of high pressure, and it's going to flow into the area of low pressure right there. Okay, that's great, but hopefully you drew those in kind of light colors or light lines, because the air doesn't actually take that path. Why not? Because as we said before, the Coriolis effect causes any fluid, whether it's air or water, to deflect off to the right. And so this straight line going across right here, right from high to low, is actually going to be bending to the right. That's going to be bending to the right. This guy is going to be bending to the right. To the right, to the right, to the right, and so forth. Similarly, on the right-hand side, the wind wants to flow right to the center, is going to flow to the center, but it's going to swirl off to the right because of the Coriolis effect. All right, and so we have these 2 pressure areas right here, one high pressure and one low pressure, and wind is going to want to swirl in one direction or another. On the left-hand side, it flows outwards. And what direction is that? Clockwise, right? Kind of like that. We call this an anti-cyclone. I should have made that capitals, I guess, but anti cyclone. On the other hand, a cyclone, which is over here, air always flows inwards. And what direction is that? Well, it's generally kind of a counterclockwise direction right there. We're going to focus more on cyclones rather than anticyclones. Because they're more important? No, but because we actually see effects of these. We're going to see a little bit later on how low pressure causes us to see storms, to see condensation and wind and rain and all that stuff. We see cyclones just about as often. Well, we experience them just about as often, but we don't see them as much because this high pressure air actually results in nice weather, clear skies, all right, brisk wind, and so all that stuff is invisible to us, and we don't really see that as much. It's really the storms that come out of these cyclones right here. And so cyclones, this inwards counterclockwise spinning, is what gives the hurricanes and other mid-latitude cyclones the shape and wind direction that we see. So that's a little bit about wind direction around cyclones and anticyclones. And we're going to head back to our notes right now, and then at the end I'm going to finish up with the Simpsons video on the Coriolis effect. Okay, well, back to our notes. There are really two different kinds of cyclones, as we're going to mostly be focusing on here, these centers of low pressure right here. We've got tropical cyclones, all right, those that form under over warm water, or it could even be subtropical ocean water as well. But it's that warm water that feeds it, and as we'll talk about a little bit later, that's what gives it the energy to keep going. So somewhere between 5 and 20 degrees latitude. So very close to the equator. All right, the center of the cyclone is warm, and again, the warmth we'll see later how that causes it to keep going. The various different kinds of cyclones can be what we call tropical depressions, tropical storms, or hurricanes. This is actually sort of a building up of names right here. Tropical depressions are lowest, then tropical storms and hurricanes are the strongest right here. By the way, depression right here, of course, we don't mean depression as you might think in terms of people, but depression meaning low pressure. All right, so low pressure, this is even lower pressure, and this is even lower pressure right here. The lower the pressure, the more the air rushes into the center and creates those high winds. All right, like I said before, the warm ocean water is what feeds it, and as water is condensing, that is going from gas to liquid, right, to water, latent heat is released. We talked about latent heat earlier on. That latent heat is what helps drive those winds. What we mean by extratropical cyclones is kind of where we live, right, in sort of the mid-latitudes. All right, they can form over land, not necessarily just water right here, but it's somewhere between 30 degrees latitude and 70 degrees latitude. And it's not so much because of the warm water or because of water at all, because it can form over land, but it's really because of fronts, warm fronts and cold fronts that kind of interact. And we're going to see a little bit later on, we're going to do a sort of a diagram and see how these air masses interact to create what we call extratropical cyclones. They can produce heavy rains and windstorms. They can even produce snowstorms and blizzards as well. So it's not necessarily like a hurricane. You've never seen a hurricane with, or very rarely do you see a hurricane produce snow. But these are the kinds of storms that we are used to, the big sorts of storms that roll across our continent. And in fact, we're going to refer to this as a mid-latitude cyclone. We're going to call it extratropical for now, but the other name for it is a mid-latitude cyclone. And so instead of deriving energy from warm water and warm air, they really derive their energy from the temperature contrast along fronts. And like I said, later on we're going to see how those fronts interact to create the mid-latitude cyclones. I think I mentioned this a little bit before, but the cyclones that we're going to be talking about can come in different names. Sometimes we call them nor'easters. That's what we would actually see in the mid-latitudes right here. We've experienced those where we live before. I mentioned hurricanes. Of course, we know about hurricanes. Typhoons, usually in the North Pacific near Japan and near Asia. And cyclones, again, kind of confusing because cyclones is a generic name, but also a specific name as well. Cyclones are really just in the Indian Ocean, south of Asia. And so we rank all these storms based on what's called the Saffir-Simpson scale. And that's this right here. Mostly, it's ranked according to wind speed. All right? But much like the Fujita scale or the enhanced Fujita scale, there are certain types of damage that are associated with each ranking on the Saffir-Simpson scale. So it's similar in that regard. It used to be that hurricanes, as we usually get around here, were only given female names for whatever reason. But they've become more common in recent decades that they started calling them with male and female names as well. But even so, there's only a small percentage of storms like this that are given names. Sometimes they're like mid-latitude storms are named after kind of how they originate, like the perfect storm or superstorm Sandy. Well, that does have a female's name too, but they're not always named. They are named by the World Meteorological Organization. All right, so every year they come up with a list of names. So they go through the alphabet alphabetically. Not every letter is used. Like for example, X is not very common. But most of the letters get hit, and so there's around 20 or so different names. And then if they run out of names, as they did a few years ago where we had so many hurricanes, they started, I believe they started calling it by Greek letters, alpha, beta, gamma, and so forth. All right, so once the wind speeds exceed 63 kilometers per hour, or 39 miles per hour, then it's given a name. All right, names are given sequentially and alphabetically each year from the list that they create ahead of time, and they do use male and female names right now, even though it used to be just female back in the 60s and 70s and early 80s. And you would think after a while you run out of names, and that's certainly the case. And so every 6 years they do recycle names. But if there's a really, really powerful storm or a really historically significant one, they retire it. For example, you're never going to have a Hurricane Katrina again, or at least not named Katrina again. So that's how we name storms. So this has just sort of been an intro to hurricanes and cyclones in general. And the next section is going to be, of course, section 2. But that's it for section 1 right now. Thanks for following along. And if you have any questions, make sure you come and see me, and we'll make sure we clear them up. Thanks. I'll see you on the next one.